The imaginary unit as well as the set of complex numbers have a rich history as well as a vast application. But in this discussion, I will not be talking about its history nor its application. What we're going to be doing here will be to construct the imaginary unit I and the set of complex numbers. If you ever study or encountered the imaginary unit or the set of complex numbers, chances are you might encounter them as definitions. But have you ever wondered where did those definitions came from? How did mathematicians came up with those definitions? When I am still studying math and we have to make a proof for a certain mathematical statement, we can use definitions without any need to provide a proof. For those definitions, unlike if you have to make use of a theorem, where a proof of that theorem was not presented in class, we have to make a proof for that theorem. But when I read a book in set theory, it was kind of fascinating how a certain action was used and a certain lemma was proven first before a definition of a certain object was established. So the idea for this lesson was quite similar to that. We have these definitions, which definitions for imaginary unit and complex numbers, which I bet you are already familiar with. And what we will gonna do in this lesson will be to trace back how to come up with those definitions, and of course to construct them. Now, consider this very simple looking quadratic equation: x squared plus 1 is equal to 0. The question is, does the solution set for this quadratic equation lies within the set of real number? Well, what do you think? Now, note that this x squared plus 1 is equal to 0 can be rewritten as x squared is equal to minus 1. We will now gonna be using proof by contradiction. So suppose that x, the solution for x squared plus 1 is equal to 0, lies within the set of real number. Exhausting all possible cases, all possible values for x in R, whether x is equal to 0, x is greater than 0, or x is less than 0, observe that x squared is either equal to 0 or greater than 0. That is for all values of x in R. The square of x is always greater than or equal to 0, which is a contradiction because we suppose here for the first part that the square of x is equal to minus 1. Since we come up with a contradiction, that only means that our initial assumption that x is an element of R is false. So, in x squared plus 1 is equal to 0, x is not an element of R. What we're gonna do within this lesson will be to construct a number set where the solution set for this equation lies. But to do that, we have to review the following. The first concept that we're gonna recall is the concept of a so-called zero divisor. So a zero divisor is a non-zero element A of a commutative ring R such that there is a non-zero element B in R with A times B is equal to 0. Observe that both A and B are both non-zero, but then the product is equal to 0. If you are used to working within the set of integers, reals, and rationals, this definition might be counterintuitive simply because of the fact that zero divisors need not exist within those set. Nevertheless, there are sets where zero divisors exist. One such example of a so-called zero divisor is that consider 2 mod 6, which is non-zero, and then 3 mod 6, which is non-zero. Take note that when you take the product of these two non-zero element of a certain set, their product will gonna be 6 mod 6. And take note that if we have 6, we divide it by 6, we're gonna get a remainder of 0. As you can see, both 2 mod 6 and 3 mod 6 are zero divisors. Um, we have here a non-zero element multiplied to another non-zero element, which gives us a product which is 0. So these are examples of a so-called zero divisors. If you want to be specific, there's a so-called left zero divisor, there's a so-called right zero divisor, but whenever you are dealing with a set which is commutative under multiplication, you can just simply call it a zero divisor. Now, for the second thing that we have to recall, it's the concept of a field. So a field is just simply a set F equipped with two binary operation, addition and multiplication. F is non-empty because it contains two elements. And then aside from that, it also satisfies the following properties. So the first four are properties for addition. So we have commutativity of addition, associativity, existence of additive identity, and then for every element in F, the so-called additive inverse is also in F. Then the next four are for multiplication. So we have commutativity of multiplication, we have associativity, and then there's also a so-called multiplicative identity. And then for the fourth property, we're gonna use this property twice later on with our proof. As you can see, for every non-zero element in F, there's a so-called multiplicative inverse of that x, which is also an element of F. And as you can see, it satisfies the property that if we have x multiplied to its multiplicative inverse, we're gonna get the multiplicative identity, which is 1. Last but not the least with the properties of a field is the distributive property. The distributive property must also hold. Now, connecting the topic of a zero divisor with the topic of field, we have this theorem which states that a field has no zero divisor. Recall that the set of rational numbers and the set of real numbers are both field. It has an algebraic structure of a field, and this is why you didn't encounter zero divisors there, because the set of rationals and reals are field, and by this theorem, those sets with a field structure doesn't have any zero divisor. To start with the proving proper, we have this biconditional statement, which states that this ordered triple, which consists of r squared, a vector space, and then we have addition, the vector addition, and then we have here a multiplication. This multiplication is very different from the usual multiplications of the set of real number. It's a different one, and later on we will gonna define how this multiplication can be done. So consider this ordered triple to be a field if and only if there exists a vector z in r squared such that taking the square of that vector gives us a value of -1. We will get to prove the first part, which is if there's ordered triple is a field, then we have to construct a vector z, which is an element of r squared, such that z squared is -1. So we will gonna focus first on that part. So let this ordered triple be a field, and let z be an element of the set of real number. Since z is a vector, we can choose a basis vector and rewrite C as a linear combination of that basis vector. So without loss of generality, we will gonna choose the standard basis vector e sub 1 and e sub 2 and rewrite C as a linear combination of those standard basis vectors, such that A and B is an element of the set of real number. Now, note that Z cannot be equal to 0, simply because of the fact that if we choose Z to be equal to 0, remember we are doing the construction here, so if we choose Z to be equal to 0, note that taking the square, since this is a field, if you have Z times Z, which is the same as 0 times 0, that is technically equal to 0, which is not what we want. So suppose that Z is not equal to 0. Remember that? And since E is also a vector which is an element of R squared, and since this ordered triple is a field, a multiplication of E sub 2 to itself, which is E sub 2, which will gonna give us E sub 2 square, is defined. And that only means that this E sub 2 raised to the second power is also a vector in R2. If that is the case, since that is the case, we can rewrite E sub 2 square as a linear combination again of the standard basis vector in R2, giving us E sub 2 square is equal to C times 1, which is just this vector, plus D times E sub 2, which is the other standard basis vector, such that C and D is an element of R. Now, since this the ordered triple is a field, taking multiplying Z by itself, which is just Z2, is also defined. And note that you can do that. You can multiply Z times Z together, and then just rearrange the like terms. It would gonna give us this. Just multiply Z, so we have A times E sub 1 plus B times E sub 2 to itself, and then you're gonna encounter an E sub 2 square there. Just what they call that, substitute this value. It will gonna give us Z squared is equal to a quantity A squared plus CB squared times the vector 1 plus 2 times AB plus DB squared times E sub 2. Our goal here, since we are doing the construction of this Z, is that what we aim to do is that make this part and let it be equal to 0. And then this part, we have to show that it will gonna be equal to minus 1. Note that since our aim here is to put this part, not the E2, just this, the one on the parenthesis, to be equal to 0. So we have 2a b plus db squared. We want it to be equal to 0. Observe that this could be rewritten as b times 2a plus db, which is equal to 0. It's always missing one bar. Now, observe that b, a, and d is an element of the real numbers. It's a field. That is the algebraic structure of the set of real number, which basically means that so there is no zero divisor. That means so we can have b, which is equal to 0, or 2a plus d times b is also equal to 0. Observe that if we take b to be equal to 0 and then substitute this to this z squared, this would gonna give us 0, but then we're gonna get so we're gonna have this term to be equal to 0. So basically, if we have b which is equal to 0, what we have is z squared is equal to a squared. Okay? That is the case if b is equal to 0. But since a is an element of the real number, taking the square of a gives us a value which is greater than or equal to 0, which is not what we need, because what we need here is to have z to be equal to a minus 1. So take b to not be equal to 0. So what we're gonna do is let b take b which is not equal to 0. And then simplifying this part, we're gonna get this value. A is equal to minus b times d over 2. That will gonna give us this 2 times ab plus db squared to be equal to 0. And note that b should not be equal to 0 as well. Now, simplifying this, so we already have a value for a, and observe that b should not be equal to 0. And then substituting this to this value, we're gonna come up with c squared is equal to this. Now let us have z squared which is equal to this expression. Our new aim here is to make this part be less than 0. So we have to show that d squared over 4 plus c is a negative number. Okay? Remember that, because for the next slide, that is what we were gonna do. Now, what do you call that? Transposing this expression to the other side, we will get and then simplifying it, we're gonna have we have this expression times this expression which is equal to 0. So we'll just have to transpose this part and then factor it out. It will gonna give us this equation. Okay? Now, remember that from the previous slide, we say that what we want is to show that d squared over 4 plus c is less than 0. Now we will gonna use proof by contradiction. So suppose for contradiction that d squared over 4 plus c is greater than or equal to 0. We have to come up with a contradiction later on. Okay? Now, for the first case, let d squared over 4 plus c be equal to 0. Then, taking the square root of that of this expression, which is also 0, and then multiplying it by b, which is non-zero, will gonna give us a product of 0. Thus, remember that we have an equation z minus b times the square root of d squared over 4 plus c times, pardon my writing, z plus plus b times the square root of d squared over 4 plus c, which is equal to 0. Since this part is equal to 0, that means this is 0, this is 0, which gives us c times z. But note that with our first slide, the slide before this, can you still recall the assumption that we have that z is not equal to 0? Right? Can you recall that? So, due to that, we have z which is non-zero, then z again which is non-zero, but then the product is 0. This is a contradiction. Why? Because we assume that z is an element of r squared, and we assume that r squared equipped with this vector addition and a certain type of multiplication is a field. Now recall that we have a theorem before we deal with the proof that a field doesn't have a zero divisor. Okay? That is why we have a contradiction here. Because z here is a zero divisor. Z here is also a zero divisor, yet z is an element of a field, which is a contradiction. Now let's move on to the next case. If we let d squared over 4 plus c to be greater than 0. Note that z is equal to this. So can you still remember how we come up with the value of a with the previous slide? Just substitute that to get this value. Note that z is not equal to this, and z is also not equal to this. Okay? Now the only way for us to have this to be equal to 0 or this to be equal to 0, either of the two, for either of the two to be equal to 0, is that if z is equal to this or if z is equal to this. But then we have z here which have this value, and clearly they are not equal. So since this is not equal, z is not equal to minus b times the square root of d squared over 4 plus c, nor this 1, nor z is equal to b times the square root of d squared over 4 plus c. Neither of these two is equal to 0. Okay? Just as the same as the first case, we have okay, but this times this is equal to 0. If you can still recall on the first slide when we simplify the z squared is equal to something. But then this is non-zero, this is non-zero, but then the product is 0. That means this is a zero divisor, this is also a zero divisor. So for both cases we have this contradiction. Now, since we both have a contradiction, that means for both cases we have a contradiction. That means this initial assumption that d squared over 4 plus c is greater than or equal to 0 is false. So its negation is true. So we can say that d squared over 4 plus c is less than 0. Now we will gonna take minus d squared over 4 minus c to be a so-called multiplicative inverse of b squared. So if you can still remember, b, c, and d is an element of the set of real number, and the set of real number is a field, and multiplicative inverse for every non-zero element, b is non-zero, therefore b squared is also non-zero. Okay? Now, since this is non-zero, a non-zero element of the set of real number, which is a field, so it also has a so-called multiplicative inverse. So we will gonna take this value to be the multiplicative inverse of b squared. Now, observe that our z squared, which is equal to d squared over 4 plus c, times b squared times this standard basis vector 1. And observe that rewriting this, just extracting out the negative 1, will gonna give us minus negative d squared over 4 minus c. We just simply take out the negative 1 times b squared. And since this and this are multiplicative inverses of each other, we can simplify that and make this part be equal to 1. Okay? Because that is the definition of a multiplicative inverse. So if you have a number multiplied to its multiplicative inverse, it will gonna give us the multiplicative identity, which is 1. Thus we have here minus 1, because we have a minus 1 here, minus 1, minus, and then we have 1 here, times 1, which is the vector 1, will gonna give us minus 1. And that is how the construction for this z whose square is a minus 1 could be done. Now we will gonna prove the latter half, which states that if we have a z which is an element, this vector which is an element of r squared, such that z squared is equal to minus 1, then this ordered triple is a field. Okay, now suppose that z is in R2, and then z squared is equal to minus 1. We will gonna take, because we have here a value, we will not be we're gonna take a z to be a linear combination again of e sub i's, but then take this to be equal to 0. What do you call that? The scalar of e sub I is 0, and then the scalar of e sub 2 is 1. So z is just the same as e sub 2, which is what do you call that? The standard basis vector for R2, one of the standard basis vector. So if we were gonna take the square of e sub 2, which is just the same as the square of z, it will gonna give us a minus 1. Now we can now define the multiplication in R2. If you can still remember, I have stated a few minutes ago that the multiplication in R2, the multiplication here, is different from the usual multiplication for the set of real number. Okay, now we will gonna a few moments ago we take a look at z as a vector. We will now gonna take a look at the elements of R2 as ordered pairs. Okay, so take the ordered pairs AB and CD, which is of course an element of R2. Note that we can rewrite AB and CD this way, respectively. Okay, now multiplying A times B times, multiplying AB times CD will gonna give us this. Okay, you can do that on your own if you want to, and observe that we have here e sub 2 square, but we have a value for e sub 2 square which is equal to a minus 1. Simplifying, we have the following, and then combining the like terms, so we have AC times minus B times D. So we have here this expression, and then combining these two and then extracting out the e sub 2, we have the following. And note that we can rewrite this as an ordered pair AC minus BD and AD plus BC. And this is how the multiplication in R2 is defined. Okay, take note of that. For vector addition, this is just the component-wise addition. We just add the both the first component A plus C, and then the second component B plus D. Okay, note that both are binary operations. So we have A, B, and CD, which is an element of R2, and then the product is also an element of R2. The same with this, we have AB and then we have CD, which is also in R2, and then their sum the vector sum is also in R2. So this addition and multiplication in R2 are both binary operations. Note that R2 is non-empty because it contains a z. Okay, now we will gonna prove we're gonna use the field properties and take a look, then prove that the field axioms hold for R2. But I will not gonna be doing it step by step. This is pretty straightforward because you're just gonna have to use the properties for the set of real numbers, which is also a field. So observe that if we have this AB plus CD, which is just the vector addition, we have this, just simplify, and then just since A and C is an element of the set of real number, and we know that the set of real number is commutative under addition, we can just simply rewrite A plus C as C plus A. Then the same reasoning will just gonna hold for the other properties. So I'm not gonna discuss them one by one. It's pretty straightforward. It's long, but it's pretty straightforward because you're just gonna have to use the properties for the set of real numbers alone. And of course, use the definition for vector addition and the multiplications that we have defined a few moments ago. So it's just long, but it's not really complicated. So I'm not gonna be doing this one by one. Okay. So this ordered triple r squared plus equipped with this vector addition and then this multiplication that we have defined is a field. Now both directions has been proven. So this ordered triple, if it is a field, if and only if there exists a z in R square, such that this the square of z is equal to -1. One moment. Now this z that we have constructed, we will just gonna give it a specific name. We're gonna call it the imaginary unit, and let I be the symbol for that imaginary unit. And that's it. That is how the imaginary unit could be constructed. Now, observe that we have this I, which has already been defined as a number whose square is equal to -1. Now we will gonna adjoin this I to the set of real number. Okay. Now, by adjoining this to the set of real number, it's just the same as taking all the linear combinations of A times E sub 1, which is just equal to 1, plus B times E sub 2, which is a standard basis vector of E sub of R2. And note that this is just 1, so we could come up with A plus B times something. Now recall that Z, which is now we call I, is equal to E sub 2, which is equal to 0, 1 from the previous slide. So basically this E sub 2, we can rewrite this as I. In that, is just the familiar set of complex number. And that's it. That is how the set of complex number could be defined. With the following properties for addition and multiplication. So we have a plus bi plus c plus di is just component-wise addition, and for multiplication, we just use the multiplication that we have defined a few moments ago. Observe that rather than using e sub 2 or 0, 1, we use I already. Now, going back to the motivation, we have x squared plus 1 is equal to 0, which is just the same as x plus I times x minus I. You can actually check this one if you want to. Just do this multiplication, use the property that I squared is equal to minus 1, then we're gonna come up with x squared plus 1. Now, since we already have that, so we can say that x is equal to minus I or x is equal to I. And we know that this solution for x, the solution set for x, is an element of R adjoint I, or just simply the set of complex number. So this is the set where we can find the solution set for this quadratic equation. And that's the end of this lecture. So thanks for watching and subscribe for more videos.